I'm going to give you a series of talks on diffraction and the interpretation of diffraction data using modern techniques. I'm going to try and give you some of the theoretical background, but at the same time not to go too deeply into the theory, because I don't want you all falling asleep. I wanted to keep it nice and simple so that you can follow, but also to give you some practical advice when you start collecting diffraction data, how you can interpret it. So this first lecture will be just a little bit about the diffraction theory, and then the later lectures will give you some information about diffraction applied to single crystal data and also to powder data. And then I'll finish off my lectures with Rietveld analysis, which is something that a lot of you may start to use. So, we're not the first, of course. Diffraction has a long history. So if we go back to 1895, you can see Röntgen discovered this new form of radiation, which in many countries they still call artium Röntgen rays, and which we in English, because in English, why were they called X-rays? Because X stood for the unknown in mathematics, so they said X because we don't know anything about this radiation, so they became X-rays. So he won the Nobel Prize for this in 1901, and then not very long after that, in 1912, von Laue demonstrated diffraction by X-rays. He took some copper sulfate, a crystal of copper sulfate, and he got this diffraction pattern from the copper sulfate. So that's a very simple experiment. We still, to this day, we take very similar kinds of photographs, these Laue photographs. And again, he won the Nobel Prize in physics in 1914. The main conclusions from von Laue's work were that crystals were acting upon X-rays in the same way that a diffraction grating does on visible light. So we're seeing a diffraction phenomenon occurring. And in order to do that, the wavelength of the X-rays has to be similar to the spacings between the atoms. And this is the first, if you like, physical evidence of the interatomic spacings of the crystal. And then in 1913, father and son team, both called William. So William H. and William L. Bragg took von Laue's experiment and they explained the diffraction phenomenon in a way that could be easily understood. They interpreted diffraction at that time as analogous to a reflection, just like you look in the mirror. So what they said, what they reasoned was that the atoms in planes within the crystal, and that your X-rays, the X-rays are being reflected from those planes. And so they came up with a mechanism for understanding the spots that we saw in von Laue's photograph. And again, Nobel Prize for Physics in 1915. So this is a story of a lot of Nobel Prizes. This is about 100 years ago, people were starting to understand this phenomenon. Then in 1914, Paul Devine and Paul Scherrer develop this technique for powder diffraction. So this is just at the beginning of the First World War in Europe. And this was also invented independently by a researcher called Hull in the United States. But the camera that they developed, this Debye-Schurer camera, was still in use up till quite recently. So this was developed in 1914. I used one when I was a PhD student occasionally. So that was 20 odd years ago. So still people were using it. And this geometry, this Debye-Schurer geometry, is still utilized in some diffractometers. So what are X-rays? So X-rays are part of the electromagnetic spectrum. So this distinguishes it from particle radiation, like neutrons or electrons, which can have similar wavelengths. So it's not particle radiation, it's part of the electromagnetic spectrum. So they lie in between gamma rays and ultraviolet. And their wavelengths range from about 0.1 to 100 angstroms, but we're typically in diffraction using X-rays of about 1 angstrom, because 1 angstrom is about the distance between two atoms in a crystal. So the amount of scattering by the electrons so the X-rays are actually scattered by the electrons that surround each nucleus, and so the amount of scattering that you get depends on how many electrons you have. And so you can define a scattering factor F, and we'll look at this in more detail in subsequent lectures. This scattering factor F is defined as the amplitude of the scattering wave in terms of the scattering power of 1 electron. Well, don't worry about too much what that means. What it works out as is that the number of at sine theta over lambda equals 0, so that's at 0 angle. The phosphorus will have a scattering factor of 15 equal to its number of electrons. Lithium will have a scattering factor of 3 equal to its number of electrons. So at sine theta over lambda equals 0, the scattering factor F is equal to the number of electrons. Now what that means is that X-rays are much, much more sensitive to heavy atoms than they are to light atoms. And this is something that you have to take into account when you're analyzing diffraction data, and particularly when you're trying to solve a crystal structure. And we'll look at that as well. So most of you will know Bragg's law. It's something that certainly in our institution we teach in the first year of the chemistry program. But just to go over it, just to make sure that you're familiar with things, if you take, for example, 2 parallel planes of atoms in the crystal, separated by this distance d, and incident to those planes are 2 parallel X-ray waves. So if you imagine this wave hits the upper plane, and this wave hits the lower plane. This second wave has to travel an extra distance before it's reflected. So the path difference between the waves is given by twice this value, and that's just simple trigonometry. Trigonometry will tell us that the path, that value x, is equal to d sine theta, and so the difference in path between this one and this one is 2d sine theta. So that's basic trigonometry. Now, because the X-rays are waves, they can do things like interfere with each other. So in order for us to see the emerging X-ray coming out of the crystal and appear as a spot on our diffraction photograph, they have to interfere constructively. That means they have to reinforce one another, as opposed to interfere destructively, where they cancel each other out. So all that means is that these waves must be in phase with each other. So the difference between the maxima has to be the same, and they should be exactly aligned. And when you get that, you get reinforcement of the waves. That can only happen when this difference is equal to an integral number of wavelengths. It can only happen if I shift this by a whole set of wavelengths. So constructive interference only happens when we get some integer multiplied by the wavelength. So n we'll call the integer, and it is formally known as the order of diffraction. That was Bragg's original formulation, and still most students know it in this way. But in fact, when we're dealing with X-ray data from a modern diffractometer, we take n into account by giving the by specifying for the particular d-spacing and the particular angle the Miller indices. The Miller indices correspond to the index along the A, B, and C axes of the cell, telling us which particular plane of atoms you are talking about. And so now, this, if you like, is the modern form of Bragg's law, and one in which we use relatively easily. Now, Bragg's law, if you apply it, if we have a look here, the H, K, and L, well, there are an infinite number of H, K, L combinations. So we can, so H, K, and L, the values of H, K, and L are integers. So we can have from 0 up to infinity. And so there are an infinite combination of H, K, and L. In reality, the number is actually limited because the value of theta becomes as the spacings in the crystal get closer and closer together, the value of theta gets larger and larger and larger, and so there's no difference as you increase the angle. Those values all sort of converge, and so in reality, it's dependent upon the value of lambda, because this is a non-linear relationship, how many of these reflections you can actually see. In addition to that, the symmetry of the cell dictates that certain kinds of reflections will not be there. Now that's extremely important for us in determining the crystal structure, because they give us information on the space group. Which reflections are absent can tell us which space group we have. So let me explain that to you. Let's take, so the types of symmetry that give rise to systematic absences arise from things like centering. So if your unit cell is centered, for example, in this case, we have a body-centered cell. The greatest of pens, but well. Another one? Oh, maybe this one. Okay. Let's see how that works. Slightly better. Okay, so if we take a body-centered cell, a body-centered cell, and you imagine, for example, in this cell we'll put some atoms of origin. So body centering just tells us that there is an extra point of origin in the middle of the cell. So an extra point of origin means an extra point of origin for all of the symmetry within the cell. And there are lots of different types of centering. So we have, this one is body-centered, it's given the symbol I, but there's also C face-centered. There is A face-centered. B face-centered. F centering, that means that there's an extra lattice point on every face, so that's face centering. And finally, you have R for rhombohedral centering. So all of these conditions will give rise to systematic absences. There is another case, which I'll talk about in a minute, but let's have a look here. Why does it happen? If we look at this primitive cubic cell, so a primitive cell, given the symbol P, does not have this extra origin. Oh, thank you. Oh, that's okay. This doesn't have this extra point of origin in the middle. So we'll just look like this. So that would be a primitive cell. If we look at the 001 set of planes, now what are the 001 set of planes? Well, if we make this A, and this B, and this C, and this is our origins here. So A, B, and C. So the 001 set of planes would correspond to this. That would be 001, and the distance would be just the distance between these two sets, so they're D001. So we can see the 001 set of planes, no problem. If we look at, we can also see, if we wanted to, in this cell, the D002. So D002 in the same cell would be halfway along here. So that would be D. So this distance here now would be D002. This one would be D001. Both of those reflections will be present in this primitive cell if we were to take the crystallography, take the diffraction pattern. But what happens in a body-centered cell? In a body-centered cell, what we've done here with our extra lattice point is actually, remember, it's another point of origin. So, in fact, what I have, if you like, I can describe body centering like this. I actually have another, so let's do it like that, another unit cell like this. So if you like, this has got two interpenetrating unit cells, both of which we could describe as primitive cells that interpenetrate each other. So there is actually no difference between this plane and this plane. The same number of atoms in both planes. What that means is that I have exactly the same type of plane as I have here, the same level of scattering I have from this plane as from this plane. But the distance between them is exactly half. What does that mean? That means that if I have two waves like this, then if that's the 001 wave, then the 002 wave will be like this. It exactly cancels out. And so in this way, in the case of in the case of a body-centered cell, we destroy, we interfere with the 001 set of with the waves from the 001, and we destroy them. And we don't see that emerging. So 001 in the diffraction pattern, so if we take a simple diffraction pattern, if this is 002, 001 is not there. So it is systematically absent from the data. And it's not just 001, but all kinds of other reflections that are related in the same way. And this type of systematic absence occurs for, these are called general systematic absences. And so for the different types of centering, they're called general because they affect all of the reflection data. So all types of HKL. So for example, in the case of body centering that we've just looked at, the condition for absence is H plus K plus L is equal to 2n plus 1. What does this mean, 2n plus 1? It means if H plus K plus L is an odd number, it's not there. So what does that mean? That means for, let's write this out. That means for body centering, we can get 1, 1, 0, but we can't get 1, 1, 1. So that's a yes and that's a no. We see, we don't see 001, but we see 002. We don't see 003, but we see 004. Now, what does that mean for us? So that means that is already telling me, if I see this type of systematic absence in the reflection data, I know that the structure is body-centered. So that tells me the first letter of the space group. The first letter of the space group, in this case, is going to be I. If I don't see anything, then it's P for primitive. And if I see these other conditions, then I know I have one of the other types of space group. That's the first stage. We then look for what we call special systematic absences, and the special systematic absences affect special kinds of reflections. So these ones are due to translational symmetry. So what is translational symmetry? So, translational symmetry so there are two types. One are called screw axes. And those are rotation by 2 pi over n, followed by a reflection, by a translation. So that's the first type, and the second type are glide planes. Is a reflection followed by a translation. So, this again is very important for us. This allows us now we've already got the type of centering. Now we can check what translational symmetry there is in the structure. So the screw axis, for example, a 2-1 axis is a rotation of 180 degrees followed by a translation of a half. The glide plane, C glide is a perpendicular to B, is a reflection perpendicular to B followed by a translation. Now, when we have these types of symmetry elements present, they affect particular kinds of reflection. So the screw axis perpendicular to B, or parallel to B, is the 0, K, 0 reflections. So 0, 1, 0 is absent, 0, 2, 0 is present, for example, here. Glide planes, so if this is perpendicular to B, it's a C glide, so H0L will be absent when L is off. So you can have 1, 0, 2, but you can't have 1, 0, 1. So that will be absent. And this is a full table, so you've got there in your handouts. I'm not sure if you can read it very well, but I will supply the original one that you can ask for and get a big copy if you need it. Okay? But this is just taken from, I haven't actually cited it, it's taken from one of the classic textbooks. This is the full list of absence conditions that you search for. So fundamentally, as crystallographers, when we first collect the data, the first thing we have to do is identify what the space group is. And we do that by identifying first the type of centering, and second, the type of translational symmetry. And you can't read this, I'm sure, and I'm sure it's not very good on there. So I will show you one. Just a moment. Let's show a big one, if I can. If I go to here. Bigger. Okay. So this is these days, if you look at international tables for crystallography, and that's like the Bible for us, as crystallographers, it's a great big book like this. And that's got these determinative tables inside. This makes life a little bit easier for us. So this gives you the types of things that you look for. So so for a monoclinic system, which is very common, particularly for organic crystals, then let's say 70–80% of organic crystal structures are monoclinic. And so these are the most complicated things that people will usually deal with. So you look for these reflection conditions. So you look for HKL, where H plus K would tell you it's a C type crystal structure. You then look for other combinations. So HOL, H000L, and then 0K0. And then from these you can work out what the different space groups are possible for your particular combination of data. That's part of your first job when you're doing crystallography. So I will just go through a worked example. It's probably easiest to do that. Oops, I'm on the wrong place. Okay, so here's a worked example. And I'm going to use just a few reflections. When I collect a real data set, I have typically thousands of reflections. But I can index this, I can index a few of these reflections and work out from, what is that, half a dozen reflections exactly what the space group is. And you can do the same. It's very straightforward. So, first of all, what do I look for? Let's look for some general systematic absences. Okay, the first thing, when we've collected the data, we get a unit cell so we know that it's monoclinic. Okay, when we actually collect the data, and in my second or third lecture, I'll tell you how that's done. So the first thing was, do we have any HKL reflections where H plus K, or K plus L, or H plus L are odd? Let's just look for them. So H plus K, here's 1, 1, 0, 0. H plus K is an odd number. So we don't have this. So that's 1, 0, 0. Tells us that we don't have that there. Then I'm looking for K plus L. Well, K plus L, here's 1, 0, 0, 1. So we don't have that, 0, 0, 1. And then I'm looking for H plus L, again 0, 0, 1 is an odd number. So we don't have that. So this must be, so this implies that this is primitive. So there's no centering. It's monoclinic. We're looking for, the unique axis is B in monoclinic. We're looking for particular types of special systematic absences now. So the next thing I want to look for is 0K0. I've got 020 and I've got 040, but I haven10 or 030. So this absence is present. So I know this is P21, at least. I then look for HOL. So if we look for HOL, the conditions are H odd, L odd, or H plus L. This would be an A glide, that's a C glide, this is an N glide. There's 3 different glide planes. So H odd, I've got 1, 0, 0, so we haven't got that. So I've got 1, 0, 0 here. L odd, I've got 0, 0, 1, so that's no good. And H plus L, again, 0, 0, 1, so that's not there. So, I don't have any other translational symmetry. This has to be one of 2 possible space groups. So it's either P21 or P21 over M. We can't use systematic absences to tell us about point symmetry. So I can't tell if the structure is centrosymmetric, and I can't tell if there's a mirror plane present. So these are the only 2 possible, and usually the way in which we would determine which one it was trying to solve the structure in either this one or this one. So moving on, we saw at the beginning that the intensities of reflections are affected by the number of electrons. We saw this diagram earlier. The scattering factor, you can see, decreases as we increase the angle. Why does that happen? Well, think about how big an atom is. Remember that your wavelength is about 1 angstrom. What's the normal size of an atom? It's also about 1 angstrom. So if you think about how big an atom is, if you look up any table, they're roughly about 1, a little bit less than 1 to just greater than 1. So an atom is also about 1 angstrom. What that means is that, consider you have what happens if you have an X-ray hitting one part of your electron cloud. And then you have another parallel beam hitting another part of your electron cloud. So we're hitting in 2 different places. What's going to happen? The same thing as we saw in Bragg's law. You're going to start to see some destructive interference. As we increase the angle, as sine theta over lambda gets bigger, you are causing more destructive interference. Your intensity is going to fall away. And that is what we see. The intensity falls away like this. So it's only at 0, at sine theta over lambda equals 0, that we see the full scattering from our electron, from the electrons in the atom. And as we increase the angle, we see the scattering fall off. How does that manifest itself in a diffraction pattern? Well, it's very obvious to see. Many of you will have seen a powder diffraction pattern already. You know that you have something like this, 2 theta, and intensity on this side, or counts. Well, what happens, you see down here, where you see some strong peaks, and then slowly, slowly you see the peaks get weaker and weaker down here. That's because your scattering is falling off like this. If you combine that with the fact that the atoms look a bit bigger when they're vibrating, okay, you see this scattering fall off depending on temperature, because the atoms vibrate more when they're at higher temperature, and this destructive interference as this increases. So that's the, if you like, the visual manifestation of this kind of fall off in scattering. So what are the main things that influence your intensity? You have the scattering factor F, which we've already described. There are also various geometrical factors. So this depends on the geometry of the diffractometer. And you can see, so if you remember Debye-Scherer's original experiment, that was just a Lindemann tube, or a tube filled with your sample, and you had X-rays coming through that. Well, that's going to vary in intensity because they'll have different path lengths through the tube. So that varies in intensity depending on that geometry. In the diffractometer you have here, you have Bragg-Brentano geometry, so it's a kind of flat plate. That's going to have very different full scattering, very different intensity variation to something that's transmission. So those are important factors. There's a polarization factor, because your X-rays are polarized. Absorption, that can cause problems. If you have a strongly absorbing sample, for example, bismuth or lead in the sample, that's going to cause problems. Thermal vibration, as I was explaining, makes the atoms look bigger. And if the atoms look bigger to the X-rays, then there's going to be more of this fall offward scattering. So your thermal vibration causes this to be weaker in intensity. And then there's extinction. So extinction is a simple concept. If you imagine your X-ray beam having been diffracted coming out of the crystal, where is it going to go? Well, you hope it will come out, but sometimes it forms the perfect Bragg angle for another set of reflections, and it gets diffracted again. And so that is extinction. So you see, some things get weaker than they should be, and some things get stronger than they should be. So these are all things you have to take into account. There are other things that you should be aware of. There are what we call intensity relationships. Now, these are all to do with symmetry. So if, for example, you have a centrosymmetric structure. So a centrosymmetric structure means that one half of the molecule is related by a center of symmetry to the other half. Or in crystallography, one half of the crystal structure is related to another half of the crystal structure. There's an important difference. You can have, for example, 2 molecules in the unit cell which are non-centrosymmetric molecules, but within the crystal structure are related by a center of symmetry. So it doesn't happen often, but it does happen. So in those cases, then the intensity of something like 111, so intensity of 111 is going to be equal to the intensity of -1, -1, -1. They have equal intensities. And there are lots of other relationships depending on what the type of crystal structure is. So for monoclinic, orthorhombic, you have these other intensity relationships. Don't worry too much about those. The main difference here is that for single crystal data, it means you don't have to collect everything. You collect just a quadrant for orthorhombic cells, for example. This is a quarter of reciprocal space, so a quarter of the reflections, which gives you enough reflections to characterize the structure. Because all of these, the rest of them, are related by this relationship, or similar relationship. What that means is, for single crystal data, it means that you can collect data much, much faster. You only need to collect a fraction of the data that are unique. For powders, it makes no difference. Because on powders, it depends on the D spacing. And usually, D111, so for an orthorhombic cell, for example, is equal to D -1, -1, -1. And so they overlay each other. And so in the powder, you just see one big peak covering everything. So, now to get to the real nitty-gritty. How do we take into account, we know about the intensity relationships, we have already an idea about what affects the intensity. But the other thing that affects the intensity is the crystal structure, of course, because that's how we use the intensities to solve the structure. So how do we do that? We do that using this thing called the structure factor. This structure factor relates the, well, we won't talk about intensities yet. Let's look how we calculate this structure factor. So for a crystal structure, this structure factor is related to the scattering factor F multiplied by this function of the Miller indices H, K, and L, and the atomic coordinates X, Y, and Z. And you sum that structure factor over every atom in the unit cell. So this is over from 1 to, if there are 10 atoms, this is a sum over 10 atoms. Now, this is a horrible looking summation, but we can make it easy. Because for centrosymmetric crystals, because X, Y, Z is equivalent to minus X, minus Y, minus Z, it's one of the conditions for being centrosymmetric, your imaginary part, that's this I sine theta, I sine 2 pi, that goes to 0. So for centrosymmetric crystals, this is actually a very simple equation. And usually in my class in London, I get them to calculate this for a very simple structure, like a body-centered cubic structure, so 2 atoms. And you find that this term just simplifies. It's very, very simple. And so this structure, why is this structure factor important? Because it's related to intensity. And it's related to intensity is proportional to the square root of intensity. But because it's the square root, and you all know that square roots can be plus or minus, we can know the magnitude. We can measure intensities. And if we take the square root of the intensity, I already know the magnitude of the structure factor, which is great. So I've got these structure factors. I can solve the structure. No, I can't get the structure directly because I don't know the sign. And because I don't know the sign, I have to model the structure. And that's what we do in crystal structure analysis. We spend most of our time working out the phases of these structure factors. So we have an observed structure factor that it has no phase, and we have to try and phase that structure factor to give us the model. And this not knowing of the phase is called the phase problem of crystallography, and it's fundamental to the crystallographic approach. So, when we're doing crystal structure analysis, we use every bit of information that we can find to try and get out the crystal structure. And what we then do is we have our observed data. We usually are working with intensity squared or FOB squared, and then we're trying to work out what the phases are by taking a model and using a least squares refinement to try and fit the observed data. One of the other things that is useful for us to know is how many molecules there are, or how many atoms there are in the unit cell. We've normally, by this stage, we've got the unit cell, but the unit cell is just a box. How many atoms are going to fit into that unit cell? How many molecules of your wonderful organic compound are going to be inside? The way we do that is by using density. And we can measure density. Density can be measured in a number of ways. Usually people use a variation of the Archimedes method. So displacement of some fluid. So that fluid can be a liquid. So you can use something called a density bottle, which is basically a little bottle of known volume with a little stopper, and the stopper, a ground glass stopper, and the stopper has a tiny hole through it. And so you tend to use a relatively non-volatile liquid, otherwise it will all evaporate. And you weigh the bottle empty, you weigh the bottle with sample, you weigh the bottle with liquid, and you weigh the bottle with liquid and sample together. And taking all of those, simple calculation will give you the volume of your solid and how much it weighs. And if you have those two things, you can, density is equal to mass over volume, as we all learned at school. So you can then easily calculate what your density is. In the case of a crystal structure, again we've got mass over volume, but the volume is the volume of our unit cell, and so as we're usually talking about a whole mole, we have to multiply by Avogadro's number. The formula weight or molecular weight, and Z, the number of those molecules per unit cell. That is the number that we need. So simple rearrangement of this equation gives us Z. Okay, and so although this is quite an ancient method, there are lots of, helium pycnometry now is perhaps a more reliable method, especially when you're working with big lumps of material. It's the same basic thing. You're looking at fluid displacement, Archimedes' basic principle. And so here's a worked example. So this is actually a crystal structure I did a long, long time ago. This is tungsten dioxide chloride. It's orthorhombic. We have a density of 4.67 grams per centimeter cubed. And these are the cell dimensions. So it's an orthogonal system. So orthorhombic, tetragonal, and cubic are orthogonal systems. So their angles are 90 degrees. So for those, it's very easy to get the volume. It's just A times B times C. So this gives us a volume in angstrom squared. Remembering that 1 angstrom is 10 to the minus 8 centimeters. So the 1 angstrom cubed is going to be 1 times 10 to the minus 24 centimeters cubed. Our formula weight, have I given it 287? So 287 grams per mole times the number of times Z, our number of molecules per formula per unit cell. Put them into our equation, and we end up with Z as approximately 2. So 2 formula units of WO2Cl2 per unit cell. It means that when I'm starting off my crystal structure analysis, I know exactly how much I should be looking for in the units. So, the last slide, just on time, is looking at diffraction techniques. And I'm going to spend the next 2 lectures looking at these 2 techniques in detail. But here, just a little comparison. What technique is good for what? And why would you use it? So we'll talk about X-rays, because X-rays are what people have most access to. Main techniques are going to be powder and single crystal. And so I've given some if you look in the textbooks about powder diffraction, what do they show you? They show you the device sharer camera that nobody has used since I was a student. Okay, so nobody uses a device sharer camera anymore. They all use modern diffractometers. So powder diffractometer is the most useful thing here. The Guinea geometry is still used quite a lot. It's a slightly different geometry. And these are the sort of single crystal equivalents. So the Weissenberg camera, the precession camera, these take different types of photographs. So fortunately, before I was a student, people started using proper diffractometers for doing single crystal work. So, I mean, in the 1960s, if you did a PhD in crystallography, your PhD would contain 3 crystal structures, 1 for each year of your studentship, because it would take you a year to collect and analyze the data. Now, I can do a crystal structure in about 1 day. Collection, analysis, and even have the paper written, almost. So it's completely different. So even non-crystallographic PhDs will have 20, 30, 40 crystal structures. So things have changed a lot here. What are the advantages? Well, powder diffraction, very good for qualitative work. If you want to know, has my reaction completed? Do I have the right stuff? Powder work is much better because you look at the whole sample. In single crystal analysis, you take 1 crystal, and of course you've got to take the best one. You know, you're going to look through you're looking under the microscope, and you will find the very best crystal. But that might be the only crystal that is the compound that you are looking for, and the rest of it is rubbish. So it's not good for qualitative work. Multiplicity of reflections we'll talk about next time. This is when you have degenerate. It's not energy, but you have reflections with the same d-spacing. Excellent resolution of thermal parameters, so you can resolve how much your atom is vibrating very, very well. The atomic parameters, if you have a choice, you use single crystal for doing your crystal structure because it will give you much better parameters. There's more data. Ab initio determinations. What is this? What does that mean, ab initio? From scratch. Ab initio, from the start in Latin. From the start, from the beginning. If you have, so for single crystal analysis, you usually start off with, here's the formula, tell me what the structure is. Okay, and that's all. So you're doing everything from scratch. For powder work, it tends to be, well, I know approximately what the structure is, let's try and refine it. So ab initio here for powder work is much more difficult. But there's no need to grow single crystals. Those of you that have tried to grow crystals for single crystal analysis know not always easy. Sometimes your powder will just crash out every time, and to get that one tiny perfect crystal can take months in some cases. Superlattices we can see more easily. Superlattice is when you have ordering over a larger unit cell than this subcell that you see. So the ordering is actually a little bit bigger, and they appear as little, very weak satellite peaks. And so that's much more easy to see in powders than it is in single crystals. Excellent resolution of cell parameters, mainly because we usually take all the data to work out the cell dimensions, whereas here we tend to take a subset, or at least until recently we did that. Nowadays we can do that over the whole data set, so we've started to see much better resolution of cell parameters here. So, as I said, the next couple of lectures we'll talk in more detail about these two techniques. Thank you very much for listening.
There's any question? Do you mind if there is question? Then
not at all. I'm happy to answer any questions.
No, I have interruption during your lecture.
Oh, I don't mind. No,
so next lecture you have something.
You can, if you want to ask something or for me to repeat something, please ask us. I hope I wasn't too fast.
Any question?
Oh, please.
My name is Amanda.
Hello.
I'm a little curious about the VNCR camera. What kind of image is that?
Oh, I can show you. I don't think I have a picture, but I can draw it for you. Well, let me show you the camera. Again. Of course, I closed the file, but... Okay. Here's your camera. And if you imagine the sample is just here in a little tube, so a little Lindemann tube or a capillary. So it's just mounted here in the middle. One of these is the entrance slit. It's probably this one because it's got the little thing to open the shutter. So your X-rays come through here. One of these acts as a backstop for the X-rays. Your film goes around the inside of the camera. And so when you develop this film, what you end up with, oops, I picked the wrong one. What you end up with is something that basically, if you imagine this, has a lot of rings like this. And so what you have to do is you take the center of the ring through the middle and you measure this distance. That distance is proportional to 4 theta, not 2 theta. So this is proportional to 4 theta. So you take into account the radius of the camera. So knowing the radius of the camera, you can work out the exact value in terms of theta between of this particular reflection. It's difficult. It relies on you. It's a manual measurement. Okay, you can put it on an optical densitometer which does it automatically for you, but it's the same, you know, in a typical powder diffraction pattern. So you're measuring in 2 theta here. So these lines, so this, if you like, is your powder diffraction pattern here. It's just that you are measuring it on film. That's what makes it a little bit more difficult. The other problem with this type of camera is that there's no resolution. So the resolution is actually quite poor. It takes about 24 hours to get a really good pattern, whereas I can collect one of these on a modern diffractometer in about 20 minutes for a nice pattern. So that's the difference. The diffraction theory is identical. You should be able to see everything on here that you do here, but here it will be better resolved. because here you're relying on the fact that your X-rays is just are just collimated. Okay, what they don't do on a modern diffractometer, you have like sometimes a focused beam. So you have two X-rays that are slightly at an angle to each other, and they converge just on your detector. It gives you very, very high resolution. So what looks like a very broad lump here in your film, you can actually resolve into K for 1, K for 2 on your diffraction pattern. So it's outdated a little bit. The geometry is still used occasionally for certain types of thing, but it's fun to use. I mean, it's fun to interpret them. I was giving this to students years ago. Here, go and have a look at, this is the diffraction pattern, measure it off, see what you get. It's hands-on. You have to spend a lot of time in dark rooms.
Does this image have relations with Scherer equation?
Yeah, the Scherer equation, okay, is really about preferred orientation.
And from the same paper.
Yeah, it's the same Scherer. The same Scherer. So the Scherer equation tells you which of these reflections, okay, will. Well, it's not really preferred orientation. It's about the width of the peak. So it tells you about the crystallite size. So the smaller the crystallite size, the wider the peak. So all that happens in this is that you have wider. So this looks a bit wider on here. The same thing here. So this would be a slightly wider pattern, like this. So the smaller the crystallite, the wider the pattern. The better the crystallinity, so the larger the crystallite, the narrower the lines. So there's also an instrument resolution factor, and the instrument resolution of this is much poorer.
So we still have actually the Scherer camera, I think in mechanical engineering. We still have a museum. So if you want to have a look,
it's worth to have a look just to see, because all the textbooks have it inside. And until a few years ago, I used to bring a my Scherer camera with me to the lectures, but I stupidly left it in the laboratory when it was being refurbished, and someone threw it out for me. So unfortunately, my museum piece is now somewhere in some skip somewhere.
Okay, with that, thanks again, Dr. Abraham. Tomorrow evening, or you have time to join our seminar at 1380, Hotel 3 in Chemistry Building at 1 p.m. So if you want to join the seminar before the lecture at 5 p.m. Thank you.